Hello, we're Team 11. WebTech was our sponsor for our senior design project for the AI Drive Efficiency System.
Wabtec wanted to increase the efficiency of their drivetrain system. In most drivetrains, an equal power input is not optimal for efficiency due to the difference between each induction motor, such as age, wear and tear, and the manufacturing differences, which in the end wastes energy, fuel, and ultimately money. Our job is to find a way with AI to eliminate this inefficiency.
By using AI and putting it into our drivetrain system, we can create a custom division of power to compensate for those motor tolerances and gain small efficiency gains over hundreds of running hours, saving money and fuel in a locomotive.
So in our study, we used a mix of different reinforcement learning models plus one supervised learning model.
The first one we use is QTable. It's a basic reinforcement learning method that maps discrete states to uh, optimal actions using a lookup table. It stores and updates Q values, which represent expected rewards for taking a specific action in a state. It provides a transparent, memory-based approach where the agent looks up the best historical response for its current environment.
Sarsa is a cautious learner that stays realistic by accounting for the mistakes of random guesses the agents make while practicing. Unlike more aggressive methods, it prioritizes safety and steady performance because it knows one wrong move could be costly. This makes it perfect for a stability model. Rather than taking big risks for a slightly better score, it stays more consistent.
DDPG, or Deep Deterministic Policy Gradient, is a foundational reinforcement learning model used to enable continuous high precision control. It utilizes an active critic architecture to map complex sensor data directly to optimal analog voltage and current outputs. It employs a replay buffer to store and learn from historical operational data to significantly improve the training efficiency and stability.
TD3 is an actor-critic model with three fail-safes. Two twin critics to prevent over-optimistic efficiency estimates by cross-checking each other. Then a target smoothing filter, which removes erratic power commands. While a delayed update ensures AI only acts on stable data. This creates a control loop that is both aggressive on efficiency and protective of the hardware.
And MLP, or multi-layer perceptron, the fundamental neural network architecture used to model nonlinear relationships between locomotive sensor inputs and the electrical outputs. It processes data through multiple layers of neurons to recognize complex patterns, such as in the engine load or rail conditions, and acts as the brain within advanced RL models, enabling AI to generalize the power settings across previously unseen operating environments.
In our testing, DDPG was the only model that scaled effectively with signal strength, seeing gains up to 2.9% on easy datasets and 1.23% on typical typical validation datasets. While MLP showed some promise, it suffered from an extremely high variance and a need for ground truth labels, while in the field there would be a lack of ground truth labels. Meanwhile, state-based models like TD3 and SARSA struggle to move past the baseline because of their safety features.
What is the real world impact of implementing an AI model into a locomotive? So, given a baseline of around 200,000 gallons that a locomotive would use per year, and at $3 per gallon, um, that's around $600,000 per locomotive per year. With If you saved 1.24% of that, you per locomotive, that's an annual $7,444 uh, saved per year. And with a fleet of 1,000 locomotives, I could save a company almost $7.5 million.
So the first tab here is a real world data generator. So here I already loaded in some network data from an API, and as you can see, you can pick from basically any 2 points, and we compute the shortest path using an algorithm, and this will take a bit here. But as you can see here, it finds the node data points along the way, and you can just save that as a file. And then here is our synthetic data generator. So as you can see, you can choose a number of scenarios. I'm going to lower it just so it's faster for the demo, and how many time steps per scenario, and also configure how many motors, the motor count, and then just some other data for actually running and creating this data. And as you can see here, we can actually use a real world data file that we generated, such as the one I just generated. And then yeah, you hit generate synthetic route and generate training data. And there you go. So we've successfully generated a synthetic data to train our models off of. Simulation is kind of just being able to run the simulation without training. And then here at training, you can see I already ran it, as training our data does take a significant amount of time. But as you can see here, you can pick how difficult of a preset you want to apply. You can choose what training data you want to choose based off. So you can see up here is the one we just generated, as well as what one you actually want to validate it on, because obviously you don't want to validate it off the training data you already trained it on, because maybe it just learned how to do really well in that data. So you actually want to validate on something else. You can select our 5 models here of what you actually want to train. It's just some other parameters, and then this is the progress bar for the run. And as you can see, here is our results from training it, because it does test it at the very end. And then go on test runs. Here I've selected just DDPG as it's our best model, and you can see the efficiency gains it has. These are different iterations of it, obviously this one being negative, but these ones being positive, and just some different data visualization for these. You can train it on different data sets, so I could select as many or as few as I wanted. And yeah. And then analytics. So this is our analytics page, where basically you can just get some basic analytics and data visualization of how our models are performing. So here's our efficiency trend, as well as comparison. Obviously I don't have any others selected, so the only one you can see is DDPG, but if I had other ones selected, they would be there. And then training iterations.